Hey, YouTube, everyone out there, thank you so much for showing up for the live show or watching the recording afterwards. If you're here live, be sure to throw some comments and thoughts into the live stream, and we'll try to make it part of the show. All right, you guys ready to kick this off?
Yep.
All right, let's do it. Andre and Aaron, welcome to Talk Python to me.
Thanks for having us.
Yeah. It's great.
Yeah, it's fantastic to have you both here. What a cool topic. Symbolic math with Python. I think I'd heard of SymPy before, but I didn't fully appreciate, how neat and how advanced it really was. So people are going to enjoy diving into this, and we can talk some internals and whatnot. And if you're doing anything scientific or computational, this is certainly a project worth checking out. But before we get to that, let's just hear your story. How did you get into programming in Python? Aaron, you want to go first?
Sure. So, as far as just programming, I kind of I've always kind of been into computers, ever since I was a little kid. Actually started messing around with programming and AppleScript in my family's Macintosh back when I was like really little kid.
Nice.
But didn't really do any serious programming till college when I started doing taking like computer science courses. And actually for Python, my college had a free course that they were offering to teach this little language called Python. So the CS course that I was taking was in like Java and C, and those languages wasn't a huge fan of those languages, but I learned about this language called Python, and I thought it was great. And so I was immediately hooked with Python, just because it's so easy to use. It's so easy to just write a program, and you don't have to worry about compilers or all this boilerplate. And then
I'd always been a little suspicious of languages that described themselves that way, which is ironic given how much I do with Python. But so often when you hear that, it's like, oh, it doesn't need all the symbols and it's super easy to get started. That means like, oh, it's really easy to do easy stuff, but then you can't do interesting things. And I think one of the things that's special about Python is like, you can keep going. You don't have to stop once you need advanced ideas. That's pretty awesome.
Yeah, it really is. You're right. A lot of languages, they kind of stop, but Python, it's got a lot of advanced stuff as well, and it's got a huge ecosystem of libraries. You can do just pretty much anything you want in it.
Yeah, for sure. The big paradox for me is there's a joke T-shirt that I've seen that says, "I learned Python. It was a great weekend," which I think is kind of true. You can do that. But at the same time, for many, many years now, I've been studying Python, and there's still just so much more to learn. One about the language, and also just like, as you said, all the different libraries, like, oh, I want to learn Pydantic now, or this other thing, or so on. Very cool. All right. How about now? What are you working on day to day?
Yeah, so I work at a company called Quansight. We do consulting, mostly around open source Python, open source data science stack. I work about 50% of my time on SymPy as part of a grant, which we might talk about later, I think. Mm-hmm. And I also work on different consulting projects. Actually, right now I'm part of a project called the Data APIs Consortium, which is trying to standardize the array API libraries for different Python array libraries, the APIs for those. So
like NumPy and Xarray and those types of things?
NumPy, PyTorch, JAX, CuPy. So the idea is that all these libraries have a very slightly different APIs, and it makes it hard to write code against that just works against all of them. So what we're doing is creating a standard API that all of these libraries will target, and so you can write code that will work with NumPy, but you can also just instead of importing NumPy, you can import CuPy, and that same code will run on the GPU, for example.
Oh, that's fantastic. Yeah, that's a really a good ambitious goal. It sounds so easy. I'm sure it's pretty challenging.
Yeah, well, I think we're being successful. We just released the first version of the specification, so and we've got several libraries that are implementing it already, including
Awesome.
NumPy, CuPy, several others. So it's actually I think it's being a successful project, and it should really help push the Python data science ecosystem forward quite a
Yeah, it
bit.
sounds like definitely a good step. Andre, how about you? How'd you get into programming in Python?
I probably at high school, I was trying to figure out when I got into it. I think at high school, I don't know, I don't remember how I found it, but it was early 2000s, I'm guessing. It was before NumPy. I think there was NumArray. I think was the array library in Python. And during my undergrad, I was studying physics. I wanted to play with mathematical formulas in Python, so that's when I started SymPy. And then I used Python, pretty much probably close to 20 years now, or over 20 years. And I cannot say I'm an expert.
It wasn't a good weekend.
I don't know. A lot of the stuff I'm not that great at, but the basics I would say I know pretty well.
Yeah, sure.
I after my PhD in physics, I went to work at Los Alamos National Lab for about 8 years as a computational physicist. And I use Python. I use a lot of Fortran, a lot of computational codes, and a lot of C++.
That sounds fun. There's a lot of Python stuff happening there at Los Alamos.
Yeah, it is. The Network X, I think, was also the library was started here. And then very recently, half a year ago, I changed jobs, and I now work at a company called GSI Technology, which is a hardware vendor, as a compiler developer. And so at Los Alamos, I started this compiler for Fortran called LFortran. It's a compiler for Fortran, but it also allows you to use it interactively, just like you would Python. It runs in a Jupyter Notebook as well as a kernel. And at this new company, we are also, in addition to LFortran, creating a new front end called LPython, which takes Python but compiles it through the same pipelines, through the same intermediate representation, and all the backends. All the code is the same. So effectively, it treats Python like Fortran. So the same speed, and so forth.
Oh, wow. That sounds awesome.
It is awesome, yes.
Very, very cool. All right. Well, super fun to be talking about SymPy with you all today, symbolic math. I want to start this off, though, with a write-up from Aaron that is maybe not what people would expect as the first topic to introduce SymPy. SymPy has been in the news a little bit for the wrong reasons recently, right? Right, Aaron? So it was even on the front page of Hacker News because this company, HackerRank, reached out to GitHub, sounds like through automated ways, and said, we seem to see some math that looks like questions we might ask or something like that. So we need to completely ban SymPy because they're stealing our interview questions or something like that, right? Give us the story. What kind of madness was this?
Yeah, so we sort of just got this notice from GitHub that a DMCA takedown had been issued against one of the pages on our documentation, and the way the DMCA works and the way GitHub's DMCA policy works is when somebody issues a notice, they basically just have to take it down, and GitHub basically took down the entire documentation site for about 12 hours. And so I've got a timeline of everything that happened here in this blog post. But basically, yeah, that they had some company that they were working with to try to find their solutions on GitHub and issued DMCA takedown notices against them, and somehow this Worth IT Solutions company decided that our docs was one of these, and they just issued the notice. And so, yeah, it ended up taking down our documentation, which immediately, like you said, it made it to the top of Hacker News and caught
Because it's so
attention.
outrageous.
Yeah, so it's the notice itself it was completely ridiculous. Like there's like the stuff that they were claiming was their copyright is like probably not even copyrightable. Like if you look at the examples on that documentation page that they took down, they're just like simple math examples.
Yeah, it was like x squared minus 2 solution is, negative plus or minus radical 2, right? Like that you shouldn't be able to copyright. I think that actually predates HackerRank's foundation.
SymPy, I think, predates HackerRank as a company.
Yeah. So the CEO of HackerRank, I guess, noticed the buzz that was being made about it and retracted the notice. So the docs ended up going back online about 12 hours later. If they hadn't done that, we would have had to issue a counter notice, which would have kept the docs offline for about 2 weeks before that counter notice would have taken effect. And that's just because of the way the DMCA law works. I also explained how the DMCA law works in this blog post. If anyone's wondering, like, why would GitHub even do this? Like, well, they're kind of required to do this kind of stuff by law. There are some ways I think they could have improved what they did here, which I go over as well. But this DMCA
It's probably
law
worth
is really...
pointing those out. Yeah. So I mean, the DMCA provides what's called safe harbor for places that host user-generated content, basically. YouTube, the social media places. GitHub clearly has a ton of user-generated content that's public. If you got the source code of Windows or something and you posted it up there, right? Theoretically, Microsoft might say, we don't really want you hosting this. It's not supposed to be open source. Please take it down, right? So that's the idea. The way it works, though, is basically once there's a request to take it down, they just have to, here's the part that I think that got missed, decide that it's a valid request and then just take it down. Like they don't really try to negotiate or determine the correctness of that assertion, right?
Yeah, so they sort of have to stay like as a disinterested third party, I guess. And the reason is that in order for them to have the safe harbor status sort of frees them from the liability on either side if there is a copyright claim or if there's a lawsuit or something. They can just say, okay, well, we're just hosting the content. The law sort of allows them to do that. But in order to do that, they sort of have to just, if they get a DMCA claim, they have to just take it down. And then if there's a counter notice issued, then they can put it back up. And the DMCA has these, the DMCA sort of tells them that if they get a claim, they have to sort of take it down expeditiously. And if there's a counter notice, they have to put it back up in 10 to 14 days. So there's a lot of parts of the law that they sort of have to do. There's some things I think that they could have done better. And there's also some things that they already do, which they don't have to do, which are nice, including they have a repo where they actually post every single DMCA notice that they've received, going all the way back to 2011, actually.
Interesting.
So you can actually see all the DMCA notices that have been issued against GitHub repositories on that repo. That it's github.com/github/DMCA.
Yeah. Okay. I want to preface this by saying I'm not a lawyer, so
and neither are we.
I'm only speculating here. But one of the things that seems very, very much like it fell through the cracks, and this part I think is both maliciousness and laziness on the Worth IT company, as well as sort of either laziness or disinterest, I guess, from GitHub. I don't really know how to characterize it, but this company came and said, on your documentations, there is content that is copyright, and it comes from our website, and it just linked just to the homepage of that other website. You got to take it down. That seems like insufficient information for GitHub to go, yeah, well, they said there's a website and here's a website. That website doesn't like this one, so it should go away. It should say, do you see these lines of code here? That was stolen from us, and here's where it originates. Or, our thing is not public, but these are the lines. They didn't even say what was wrong, right? It just said, we believe
it was insufficient even for us if it was an accurate claim. Because if you look at this page that they put the claim on, it's a huge page because it's got like about a dozen different functions on it. and it just said that they copied our examples. It didn't say which part of the page was copied or anything. So yeah, I mean, I still don't know like how they even decided that this was a thing, that somehow their automation got flagged incorrectly or something. I don't know. Like I don't know if we're ever going to know that.
Yep. All right. Well, I don't want to spend the whole time on this, but let me wrap it up with a quick thought. So the CEO of HackerRank, Vivek, posted a message that said, this was not our intended consequence. Yes, but if you send bots running around the internet looking for algebraic equations and saying that those are, like this is your problem, even if it was not your intent to do these things. And so they fixed it. I don't know what they're doing now, but they said we're going to stop the whole process for now and figure out what we can do better. But on the other hand, we should give them props for donating $25,000 to the Senpai project as a "we're sorry." That's actually kind of cool. They didn't have to do that.
No, they did not have to do that, and they did send the money, I think, last week. And so just
you guys are all on vacation. What is this, Hawaii? Or I'm just teasing.
If the finances are online, you can find them up. I think it's open on the Open Collective, and it pretty much almost doubled our budget, and so
cool.
It will allow us to really fund all kinds of cool development. One thing on this note I wanted to say is that I was thinking, so when it all started, I thought, this is I felt like a little guy completely being crushed by some huge corporation, or just this, they just take down the documentation, and GitHub just says, it's not enough to put a commit to fix it. You have to excise the commit from the Git history. So we would have to figure out exactly what line was copied. And so I went to the Git history and tried to look up, well, maybe some of our contributors maybe copied some stuff from HackerRank. It's possible. So I went to the history, but didn't see anything. Did not see any mention of HackerRank. I copied this from HackerRank. Didn't see anything like that. We didn't see anything suspicious, but the consequence was dire. And also the documentation is generated from the Senpai source code. So really, the offending lines are coming from the Senpai repository itself, not just the documentation. So they would take all of Senpai.
So luckily they missed it.
So I was like, well, this might be this is terrible. And then and also we thought maybe this looks like a spam, maybe it's just a spam. So we kind of ignored it a little bit, not ignored it, but we didn't know. And so I emailed GitHub right away. Is this real or is this just a spam? And they got back to us on Monday evening, say, no, this is real. And then the next morning they took down the whole documentation. So I felt really just, I spent, and Aaron and others spent so many hours just trying to figure out what we should do and what the options are. And it was Google Summer of Code was deadline was on that Tuesday, I think, as well. So I was just super busy with that. I just felt, this is, and I'm doing this for free for Senpai. I don't think I've ever got paid by anybody to work on Senpai. So I just felt, this is not right. And then when I got to Hacker News, I thought, I thought about how can the company, what can they do to fix it? And I thought, there's not much they can do. The time was wasted. But then Travis got an idea, Oliphant got an idea, well, why don't they donate us some money? And I thought, this would fix it. And so, I didn't think they would do that, but I'm very happy that they did. As far as I'm concerned, personally, I think we are even. They gave us the money, and we can use it to really progress the development forward. So I'm very happy that how it all ended for Senpai.
Sure, you could pay to hire somebody to work on some important part, or you could pay to have sprints, like bring the people together to work together, or something like that, right?
Mm-hmm.
Nice.
Yeah, we're still talking about what we're going to do.
Cool. Well, I'm glad it came out well, but what a wild story, huh? I've had run-ins like this before, and they are incredibly frustrating. Even when you're on the right side of it, it's just like, you're up against lawyers from.
Yeah, you're on YouTube, so I've heard that DMCA's can be pretty bad on YouTube. I don't know if you've ever been hit by anything like that there.
What's so funny is only once as it happened on YouTube. It's happened for my courses. It's not exactly, it's happened sort of almost in reverse for my courses. I put one of my free courses on Udemy as a way to try to reach out to people who didn't already know about my content. Like, I'll put it up there for free. People can experience it there, and then maybe they'll go look for other courses from me, like, something like that. Someone stole my free course, started selling it on Udemy, and it took me 2 weeks to get them to even take it down, even though at the beginning it's a picture of me saying, "Hi, I'm Michael," and they're like, no, we don't believe this is yours. Like, what do you mean? Like, have you watched it? The person who is the account it's under is absolutely clearly not Michael. Anyway, on YouTube, what has happened to me is I was doing a webcast way back in the day when people would call in, sometimes on phones, and somebody interrupted someone else on during the webcast, and they put it on hold, and it was really frustrating because their hold music started playing back into the webcast, and for some reason, the way it was set up by the company I was working with to do it, they couldn't stop it. So there was just like 5 minutes of hold music going along with the presentation. That hold music got a DMCA takedown, and it took down my webcast. So what are you going to do? I didn't really mind. It was kind of a crappy thing anyway, but it was up there and it got taken down. All right, let's talk about SymPy, because I think this is a really neat project. Like I said, when I think about the data science stack and the scientific computing stack of Python, traditionally what I've thought of is NumPy, Pandas, Matplotlib, the stuff that does numerical processing and then maybe visualizes that or does machine learning off of it or something like that. But SymPy, I think, occupies a slightly different but really important space in this whole computational Python stuff. Tell us about it.
Yeah, so SymPy, like you said, it sort of stands in contrast to these other libraries in that it is a mathematics library, but it's not numerical, it's symbolic. So the focus is on computing with mathematical expressions exactly. So if you tell SymPy to, like you said earlier, solve the equation x squared minus 2 equals 0, you'll get the exact answer, square root of 2 minus square root of 2. You won't get a numerical answer like 0.7, whatever square root of 2 is.
Yeah.
But you'll get that exactly, square root of 2. And so there's all sorts of things that you can do with symbolic mathematics. People may be familiar with other similar tools called it's called the computer algebra system. There's proprietary tools like Maple and Mathematica. There are some other open source systems that people may have used as well, like Sage and Maxima. So just if you've ever heard of any of those, SymPy sort of occupies a similar space, but SymPy's I guess sort of stands apart from those in that it's open source and it's a Python library. So if you're familiar at all with Python, it's really easy to start using SymPy because it's just Python.
Yeah, I think people who have not seen this kind of stuff in action should definitely go poke around and check it out. And we'll talk about some ways in which you can play with it just online with super low effort. I remember the first time I had been previously using MATLAB or something like that, and I saw Maple, which is one of the ones you called out, which is a symbolic sort of solving thing. You can say, oh, here, I want to do the integral from negative infinity to positive infinity of this thing. And it looks like it would come out of the textbook, and it will sometimes even show you the steps. It's unbelievable. And that was 20 years ago when I saw it. I'm like, that's unbelievable that this computer is doing this. And SymPy is like that, but for Python, which is fantastic.
Yeah. So it's basically it's the math that you would learn in a classroom. It's except it can also get very advanced. Like you said, we can do integrals. We have lots of very advanced mathematical features. We can do we have a module for doing various areas of physics, for example.
Nice, and it's also the foundation of many other things as well. Just as like setting the stage, a preview is. You've got algebra, you've got calculus, you've got differential equations, you've got linear algebra and matrices. There's a lot of good stuff in here. Andre, do you want to maybe give us a little run through of like sort of the selling points of SymPy?
Yeah, I can. And that's very easy. I was an undergrad student, and if you study physics or any kind of engineering, a lot of times, even math, you have to do a lot of symbolic, I would say derivations on paper. And I remember sitting in a physics class, and I thought, this, I would like to do this from Python interactively. And so that's the idea. And then, of course, I sat down and I thought, well, let's get started. And my friends were telling me, can you do Gaussian integrals? It's this integral of exponential of some polynomial, x squared, for example. And I said, it cannot but it will in 5 years, just not now.
That's the hard problem.
I need it now, and I said, well, then use Mathematica. It can do it now. But they asked me, well, why don't you use Mathematica? And I said, Mathematica is great. It's Maple as well. It's absolutely, as you said, Michael, absolutely amazing that 20 years ago, and it could do all these integrals and series expansion of these functions. And
yeah, I was using Windows NT when I did that. That's how old that was.
I did too, actually. And so, but the motivation is to be able to do it from Python interactively allows you to kind of almost program with the symbolics using a language that's a pretty decent language. That you might already use for something else. And so what I wanted to do is assign the expression to a variable, then use the variable interactively and write some scripts to kind of handle my calculation and maybe save it to a file after that and so on. And so that's, once you want to program with that, Mathematica, it allows you to program, but you have to learn their language. And Python, I like Python more than the Mathematica language. And so that's why I wanted to have that in Python.
Well, the other thing that from this perspective, sitting on the Python or the comp sci side of things and looking back is obvious. I don't know that it is as obvious coming from the other perspective of like, oh, I'm doing a MATLAB.m file or whatever. But in that world, if you work in MATLAB or Mathematica, you can do what MATLAB or Mathematica does, right? It's really amazing in its specialty, but it's very specialized and limited, right? You can't build like, fast API and database driven apps that are doing some of this kind of computation along the way, right? If you move it to Python, like this capability is now accessible for all the applications, not just within, the MATLAB or Maple environment.
Yeah, and I guess it's an argument, what's the advantage of Python, let's say for numerical computing, let's use NumPy, or scientific, let's say for scientific computing, what's the advantage of Python over, let's say, Mathematica? And I think it's not a clear-cut answer. I think Mathematica is great, and they've done, actually, it's quite amazing how good job they've done, because they designed the language, I believe, in the early 80s, and they did not have to really modify the language too much. In the same spirit. So that's kind of amazing. It's much older than Python. So it's quite amazing how far, and that it still works pretty well, and it's a decent language. But I think what I like about Python for scientific computing, is that it's open source, and the language just seems more kind of robust and kind of easier, more imperative, don't have to really learn too much. It seems kind of anybody can learn it quickly and doesn't seem to have too many kind of things that would surprise you.
Yeah. Very cool. So how long ago did you start on SymPy?
So I think I started it in 2005 or 6.
Nice. It's been going for a while.
Yes.
Yeah. That really predates a lot of the scientific computing frameworks that are well known today, right? So you must have felt good about picking the right horse as you saw, Jupyter or IPython at the time come along and libraries like that.
Yeah, way before Jupyter, IPython was there. Somebody told me about it, and I tested it out, and I thought, this is pretty cool. This looks like Mathematica. And then later, when I talked to Fernando Perez, who wrote it, he said, yeah, it's Mathematica. That's what I wanted to have in Python. So kind of the same motivation almost, so he kind of provided the foundation for the interactive part, with the prompt and the numbers and so on. It's very similar to how Mathematica used to work.
Nice. When you work with SymPy, we'll see some examples and talk about them in a minute. You can put it into this like pretty printing mode where it attempts with as much as it can within the terminal output to have more formal mathematical representation. So instead of like E caret X, it might put a little smaller X up high and then an E down slightly to the lower left of it, like you would try to write it. It seems that if it's in a notebook, it should be able to do even better, like maybe a LaTeX rendering or something really shiny.
Yeah, it does. So
Does it do something
in
like
the
that?
notebook, it'll use the MathJax, so it'll look great basically, because the MathJax looks just like it's the same as,
Like
as
a
the LaTeX
textbook.
document. Yeah.
Yeah.
So,
oh man.
but
That's
yeah,
awesome.
in the terminal we use all these different Unicode characters to sort of render it as 2D text in the terminal, so that it looks pretty decent in the terminal considering the constraints of a terminal.
Nice.
And I personally use it. I mainly use it in the terminal myself.
Yeah. So let's go and maybe we could walk through a little bit on one of the tutorials here. I mean, obviously, we don't want to talk too much code or whatever, but I do think maybe just touching on this will give people a sense of what it's like to work with this, because
Yeah, so I think
give us a sense of what
in the
what it
tutorial
looks like.
there's actually a section somewhere. Where is that section?
This one perhaps,
but didn't get deleted. It's in the introduction page. Yeah, it's on that page, but if you maybe scroll down to this, the power of symbolic computation is the name of the header.
There you go.
So this is just sort of a bucket list of just sort of a bunch of different examples of things it can do. So just to give you an idea, and actually you can see there, you can also see the pretty printing there as well, the Unicode pretty printing that it does.
So
that LaTeX is what you would see in the notebook.
_printing use Unicode equals true, right? It doesn't do it by default.
Yeah. So in the notebook, it does actually do it by default.
Sure, but not in the terminal or the REPL.
Yeah, in the terminal, you need to run this. Otherwise, it'll just print out like a one-dimensional string that you would get. It looks sort of like what you would input. But yeah, you can see here it can take derivatives, take integrals. If you keep scrolling down, you can see I think limits and differential equations. You can solve.
Yeah, so let me talk people through just a couple of things, because I think it's a little hard to understand how this might work. And the trick, I think, really, Andre, you tell me your thoughts on this, is the ability for it to define these symbols and these functions here.
Yeah, so the trick is to be able to represent the expression symbolically. So you type x plus y and plus some function sine x, and in memory it represents it as a tree, and it stores the expression in symbolic form. And then it has all kinds of functionality that allows you to manipulate the expression, print it, differentiate it. So when you differentiate, or let's say an expression that takes the original expression and creates a new expression, the derivative.
Right. With normal math, like pen and paper math, you don't usually define variables. Every now and then you say, let x be an element of like the real number such that whatever. But normally you just say f of x or f of t or something like that, or y, and it just works. You needed some way in Python to allow you to write expressions like x plus 2y without Python going, I have no idea what that means, right?
Yes, that's right. So, and yes, you first have to declare what x and y is. You declare it as a symbol, and then you can use it. We override the Python on operations like plus, minus, and that way you can construct the expression. And so what's nice about Python is that when I started with SymPy, when I was kind of investigating the idea, what's nice that Python pretty much allows you to override all these operations, and so you can write it almost like math. You have to do exponentiation to stars.
Yeah.
The only caveat is that if you write, let's say 1 divided by 2, especially, and we started in Python 2, that gives you 0, I believe. And that's very confusing from SymPy's perspective, because you would like it to give the expression 1 over 2, not 0. And so I don't think there is any way still to fix that, to override this division.
At least in Python 3, you get the right
At least you get
float.
5, but you get a 0.5 float, double precision float
Yeah.
number, and
Yeah,
that's,
yeah.
you don't want that. You want 1 divided by 2 as SymPy expression. So when you have something like that, you have to wrap the number 1 into an integer or s.
Yeah, or define some kind of symbol with that value, and then use it like
You have to convert.
AB from quadratic equation, right? You could like that kind of thing. But yeah, so you create these symbols, and then you can write simple math that looks like it's just straight Python. So you could say X and Y are symbols, and then you could say something like X plus 2 times Y plus 1, and that isn't not evaluated in any way. It just becomes this, like, as you said, this tree, this expression that then you can operate on, like integrate it, take the derivative of it, find the limit of it, all those kinds of things, right?
Yes, exactly.
Yep. Yeah, that's the basic idea, and you can use it to do basically any sort of math that you would normally do with that sort of expression, except you're doing it on the computer instead of doing it on paper.
You can do, just like a real simple example might be rational polynomials or something like that. Like if you had x squared minus 1 as one equation, and then x plus 1 as another equation, you could say the first equation divided by the second and get, which did I say minus that? You get x minus 1. As the result,
so simplification is another one where you can take something and it can figure out how to simplify it to an equivalent form that's like dividing out factors and things like that.
Yeah. Okay. Yeah, these are super neat. You can do factors. So like you say, you could say like polynomial factors. One of the things, I don't know if I should point this out, or maybe this should have been a warning to the whole show. If you're in high school or early college, this might be a terrible cheat sheet for homework and other types of. I mean, it's fantastic, right? If you're in an algebra course, you can do your work, and then you could type this in and go, did I get it right? Wham, and out it comes, especially in a notebook, right?
Yeah.
Yeah, I mean, I think that's kind of unavoidable these days. There's also, just graphing calculators that do this. There's Wolfram Alpha. I think SymPy is a great way to do that if you're going to do it, because now you're also learning Python, which I think would be great for someone who's like a high school student or an undergraduate, because that's an actual useful skill as well.
It might be even more utilitarian in the long run than the calculus they're learning. So yeah, you can do like derivatives and integrals of these equations. So you could say integrate e to the x times sine of x plus e to the x times cosine of x, and it will give you the result, which apparently is e to the x sine of x. I used to be able to do that. I can't anymore.
Well, you can see the line above it, it's differentiating that, so it's just undoing the line above it.
Oh, I see. Well, that does a bit of a cheat, isn't it?
Yeah, but yeah, I mean that's you don't the integration is nice because you don't have to remember all these how to do all this integration by parts or whatever you would do.
Yeah, exactly. So another thing it can do is like concrete. I forgot there's like a better term for that, but definitely integration over a range, or so you could say integrate from like -10 to 20 of sine of x squared, or here's an example of -infinity to positive infinity, and it says that square root of 2, radical 2 radical pi over 2 as the answer, not like what is that? 0.2 something. I don't know, something like that. Right. It gives you the actual theoretical answer, the exact mathematical answer in symbols, which is amazing.
It is. It's amazing, and it's also not easy to. So when I started SymPy, I knew this is not easy to program. Like how do you program such an integrator? It's not easy. But I figured, if I can at least get the basics, like be able to represent these equations at least, that would still be a huge help, because sometimes the expression can be long and be able to manipulate it. And then as we were joined with so many excellent people, they contributed all the feature students. Mostly actually it was developed by Google Summer of Code students. And
okay, that's cool.
It's I would not be able to do that. Let's just put it that way. It's a lot of work that's behind it.
Yeah, I'm looking at this. I know these concepts just on pure math are hard, and then to automate it in general, it's got to be next level. So other things you can do is like you can define a function. So here you say, here's a function called y, and then you can say, well, what if you had the differential equation that was, the second derivative of y minus y equals e to the t, right? Solve that. And then sure enough, out comes the solution for that, what the function is, which is pretty amazing. Yeah. So does things like eigenvalues from linear algebra and all kinds of stuff. Yeah. It's great. And then we have in Python, we have stir and repr. You guys also have LaTeX, which is pretty cool, right? You just call LaTeX on a function, and out it comes with like the crazy escape code LaTeX that you would need for a paper or something, right?
Yep.
Yep. Yeah, and this actually, I mean, this is only even scratching the surface of what SymPy can do. So it's actually quite a large library.
Yeah. I don't want to focus too much on just the pure math, but maybe give us a sense of like some of the things that amaze you. What do you have in mind when you're saying that kind of stuff?
That amaze me.
Yeah.
I mean, I think the whole thing's amazing still, even though I know how it works and I've been working on it for a while. But yeah, just the fact that the computer can do the same sort of mathematics that you would do on a piece of paper is incredible. Some of the algorithms that to do like integration and stuff are also pretty interesting because they go beyond what you would learn in a calculus class. They're algorithms that can compute integrals that you would never be able to know how to compute them just using what you'd learn in a Calc 1 or a Calc 2.
Sure.
But those is something that you can actually implement in something like SymPy, and then SymPy will be able to do those integrals for you. Some of the features that, I mean, if you go on the website, there's a huge list of features. I think one feature that we didn't mention that's maybe worth mentioning is code generation. So code generation means that you take one of these expressions and you turn it into basically code for another language, whether that's C or Fortran or pretty much any language that you would want to translate it into, and then you can then take that expression and basically convert it into something that you could numerically evaluate very fast in whatever language you prefer to use.
Wow. Okay. So you've got your notebook written in Python or something, and you've come up with some expressions, and you're like, I would like to just do that in Fortran or C, and I don't trust myself to get it right, so just print out the syntax, basically.
Yeah.
Oh, go ahead, Andre.
Yeah, well, let's say you want to approximate some function, with a polynomial, and so you can use SymPy to do that. And then at the end, you just want the polynomial in the form that you can put in your production code, whether Fortran or C. So just tell SymPy to do it, and you can copy and paste it, and it's correct, assuming there is no bug in SymPy.
Yeah, sure. Yeah, I suspect it's probably pretty straightforward. Once you've got the expression to break it down into, this is a multiply, here's where the parentheses that group it in the expression tree. But
yeah,
there's not simple.
There's a few places where it's like, okay, we need to make sure we get the semantics. The semantics might be a little different between like C and Python or something like that. So we need to make sure we sort of translate that correctly. But yeah, in principle, it's not that hard, but I mean, it's also not something you want to do by hand either, because
it's super error prone if you were to try to do it by hand. Yeah. It sounds like a great feature. That's quite neat. Maybe we could talk just a little bit internally, Andre, about how you accomplish this.
Yeah, like how I started it.
Well, just like how does it work? If I give it an expression of, e to the x cosine x, and I say integrate that, like where do you even start?
Yeah, exactly. Uh, well, the integration, I guess, I don't know those more details. There's like a couple different algorithms, but I'll tell you kind of the basic idea. When I did, the first thing you do, you search, how do you do symbolic integration? And there is this famous algorithm called Risch, I think, algorithm. So you kind of start studying it, and then you realize, oh, that's like multiple years of worth of work to implement this. And it's kind of fragile and doesn't always work. And Mathematica, they as the company, because Wolfram, they managed to do that. It's a lot of effort, a lot of work. They have to invest in large teams of people, test it carefully, and so on. But turns out that in practice, there are other approaches, and it turns out that you can integrate wide classes of functions just by implementing an algorithm that works. For example, for a polynomial, it's easy. Anybody
Yeah.
can do it, right? And then you can add some trigonometric functions. So you kind of implement algorithm for that. Then you kind of build your way up. It turns out when you do that, you can make it very useful in practice. Maybe it's not as powerful as Mathematica is, but it's very helpful. So that's how we started. And then
Okay. Once you have the rules, I mean, first, second, third year of calculus, in math, there is a ton of creativity. In the calculus classes, it's a lot of like, today we're doing integration by parts. Today we're doing like integration of stuff that's divided, or what, like there's set algorithms that they tell you to follow. And once you get the basics, it seems like, I guess you could compose them.
Yeah, so that was kind of my initial idea. Let's just kind of do stuff that we know how to do, and it's kind of straightforward. But then kind of the engineering part comes to it as well, because you want things to always work and quickly. And if it cannot be done, you would like to know the answer. This cannot be done quickly, not to wait a couple hours until it tries all the formulas. And so then it just becomes a lot of not kind of I would say engineering decisions, how to make this all work. And I think we are still not done yet. I think there are a couple, I would say, promising approaches. One approach is a certain professor, I think, or retired professor, I think in Canada, he figured out how to take all these rules, how to integrate functions and compose them into just a decision tree. So you give it an expression, and then it just figures out exactly as you said. Is it a polynomial? Is it like dividing and so on? And then the decision tree tells it exactly how to go about it to give you the final formula, the integral.
Okay. Here's the small formula you apply to it or whatever.
So it encodes these 5,000 formulas, and then then takes them and actually he uses Mathematica, and he composes those into a decision tree, and then it prints the decision tree as for example Python code and so on. And we still haven't, so we have a module for that. And it's something that what I like about this approach is that it's quick. In principle, it's quick. You just go through the decision tree, and it either gives you a formula or it says it cannot be done. And I would like, but there are all kinds of practical issues. The tree is pretty big, and so when you encode it in Python, it takes forever to import, and so on. So we are still kind of struggling with these issues, but it just gives you an idea what kind of issues are engineering, I would say, issues are involved in. Something like this.
That's pretty wild. Have you thought of or are you using things like Python or other types of speed up type things?
Yes. Yeah, so maybe 10 years ago, I spent a lot of time investigating how to make SymPy faster. SymPy is great. It's in pure Python. It's easy to contribute to, and for many things, it's amazing. Just works, and that's all you need. But sometimes you need either larger calculation or a lot of calculations, and it's not fast enough. So how to speed it up? So we investigated just pure C, Python, all kinds of tricks in Python itself to speed it up. Eventually, that kind of led to the SimEngine project. I decided, let's just use C++. That's the only tool that I know that actually can deliver the performance and kind of maintaining a bigger project. And so that's SimEngine, and then we have Python wrappers, and then SymPy can use it. So there are modules in SymPy, such as the dynamic the classical mechanical, I guess, module that allows you to simulate solid body, physics. Is able to use SimEngine under the hood, so it gets much faster.
Okay, interesting. Yeah, so this is a C++ project,
Yeah.
but it has Python wrappers for
Yeah,
easy Python integration with SymPy and other things.
that's right.
Yeah, that's cool. That I think that kind of summarizes a lot of scientific Python. Is there's a really great API, and when you ask it to do things, it takes the data and hands it off to some C layer that actually does it, or
Mhm.
Rust or something like that, right?
Yes. And it's not just writing in C++. There are other libraries that are also in C++, but to make it really fast, one has to spend the time and figure out how to represent the expression in memory, how to allocate the memory. So we have to make reference counter pointers, for example. So that's the design I chose.
Mhm.
How to make the reference counter pointer as fast as possible, things like that. How to make sure that you can actually maintain it so that it gives you, if you make a mistake, it doesn't give you a segfault, but some kind of a in debug mode, at least some kind of ways to debug it, right? So there's all kinds of engineering,
Yeah.
decision behind the scene.
I asked it to solve this, and it just went poof and went away. I guess that means something. I don't know.
Yeah, so we don't want that. So, but anyway, but yes, so the sim engine works. It contains kind of like the core level of the core of SymPy. So it's able to-
Is this what I would, if I go pip install SymPy, do I get this, or do I have to do something special to like swap out the computation engine with this?
you have to install it as a separate library. So if you do just pip install SymPy, by default it only installs SymPy, but you can do I think you can do pip install SymEngine. I use Conda, so you can do Conda install SymEngine.
Sure.
That installs SymEngine as a library, and in Python you do import SymEngine, and then you use it kind of like SymPy, and SymPy can also optionally use it kind of under the hood.
Okay. Yeah, this looks really neat. One of the things I wanted to touch on here, and at the top right of the page, if I go just to the SymPy page, it says try it with SymPy Gamma. And so maybe we could sort of close out the conversation a bit with just poking around with this and then maybe highlighting some projects that use it. So for example, it says, oh, you could just try some random example, and it's got like algebraic things I could do. So it says, polynomial divisor. I can come in here and copy this. And if I go, there's a little calculator like thing at the top where I go hit equals, and it will go and run that in
It's the polynomial division in this case, it looks like.
yeah, like what are the divisors of this thing, right? Something like that.
Yeah, so this is sort of our little version of Wolfram Alpha, but using SymPy under the hood. It's not quite as powerful as Wolfram Alpha. We don't support like natural language input, that sort of thing. But yeah, you can kind of get an idea of the sorts of things SymPy can do here. Maybe one of the interesting ones, if you scroll down a little bit,
Okay.
and click on one of the integral, the one that says get steps for integrals.
Yeah. How about this? I'm a big fan of E. There's a whole book called E, the Story of a Number. Have you guys read it?
No, I haven't heard of it.
You haven't? E, the Story of a Number is a great book. It's about like Euler and all that stuff. Okay. Yeah. So if this one says
if you scroll
integrate
down-
e to the x over 1 plus e to the 2x, right?
Yeah, so if you scroll down here, hopefully, you should see something that says see steps.
All right. Yeah, I see under the derivative, for example. Yeah, that was pretty interesting. I don't know if this is the one that has steps, but I saw it in other places.
Yeah, maybe that's examples. It's not working right now.
Yeah. There's some here. Let's do probably the differentiation of something might be. I bet it's got some steps for that. But that was part of what I was talking about with the cheat. and I don't mean that in a negative way, but like it will show you the steps as if it was written out in a textbook of how, like this one right here. Like, look at this. You're going to apply the quotient rule, which is dx of f of x over g of x equals this. And then you're going to apply this. And I mean, this is amazing.
Yeah, well, I mean, I think it's it's instructive. It's not just cheating.
No, of course it's not. And I do think it's really instructive because it's one thing to just go take a function or an expression and say, take the derivative of this. And it says, great, it's this crazy thing. Like, how was I supposed to know it was like the tan of the cotangent of x or like something like that, right? But if it says, like, look, here's how we got there, that's very educational.
Yeah. So it's not this many parts of SymPy don't work like this because sort of the underlying algorithms don't really work the same way that you would do it by hand. But
Mhm.
there are some that basically work the same way you would do it by hand, like differentiation is an example. So we can sort of extract those steps and show them to you.
Yeah, this is great. I'll put this explanation example into the show notes so people can come back and check it out. But gamma.sympy.org, and then just choose some of the examples is really how to do it. It's how it gets there. So very nice. So let's wrap this up by going to sympy.org. And then on sympy.org, if you go just down a little bit, there's projects using SymPy that they all sound super interesting to me. You've got like ChemPy, a package for chemistry in Python, Einstein Pi for symbolic and for general relativity. Are there any of these that you think are particularly neat or stand out to you? You want to give a shout out to? Either of you?
Oh yeah, all of them. But I like the PyDie, for example. It's a very nice package for you can
Pi dies and dynamics. Yeah.
So you can it allows you to simulate. You create kind of like a robot or pendulum, like double pendulum. You just kind of tell it exactly the relations of the body, and then it allows you to write. And then PyDie can derive the equations of motion, and those equations get extremely complicated real quick. For
Wow.
try triple pendulum, it just gets very complicated. PyDie can derive the equations for you correctly, and so it's a really neat project.
Yeah, that one's really cool.
So you can see.
The ChemPy kind of stands out for me because I've always loved chemistry. Yeah. Any others that you want to give a shout out to?
Well, I guess one that I'll mention here actually that's listed is Sage. So Sage, Sage is something that a lot of people might know as sort of an alternative computer algebra system.
Yeah, I've actually
that
had
uses Python.
William Stein on the show to talk about it as well from Sage Math and
Yeah, so
Sage
Sage sort of integrates a lot of libraries, including SymPy itself. You can see SymPy is listed there on the front page of their website.
Yep.
So if you use Sage, there's a chance that you're actually just using SymPy under the hood. So that it's
Nice.
that's one that I like. A lot of these are making use of the code generation concept that I talked about, where they're basically sort of modeling whatever chemistry or dynamics in SymPy, and then taking that expression and turning it into something that they can numerically evaluate.
Yeah. Even looks like maybe some quantum computing stuff here. All right, great. Now these are all cool, and I think probably seeing some uses of it might give people ideas for their own projects. Let's wrap this conversation up, just to talk about maybe bridging the gap or bridging the world of computational stuff, symbolic stuff, and then this numerical side, right? So I've gone through and I've said, here's some complex function, and maybe here's another one, and I'm going to combine them through whatever in some way, and then now generate me the second derivative or whatever it is I need, or integrate it. I've now got a new expression. Can I somehow take that and turn it into something I can call as a Python function? Like, here's a number, what's the answer effectively? Or here's a NumPy array, give me the evaluation across the NumPy array.
Yeah, so there's a function called lambdafy. It's LAMBDAFY, which basically does exactly what you said. It takes an expression and it turns it into a function that you can evaluate with NumPy. The workflow is basically exactly what you described. You use SymPy, derive whatever it is you're doing using the mathematics of your problem, and then you put that inside of lambdafy, and now you have something that you can actually pass your data to with NumPy and evaluate it numerically.
Nice. That's awesome. Does it effectively use that code generation thing you were talking about?
Yeah, so under the hood, it's basically generating code for
target
NumPy.
language equals Okay. Yeah.
Yeah. So
See.
I mean, you can think of NumPy itself as sort of a language. It's got its own set of functions. And
Right. Right. Instead of looping, you do sort of vector operations and things like that, which you'd want it to do that. Yeah.
yeah, there are other functions which you can do to instead of calling NumPy, if you want to like call it through C as well. There's options for that as well. Um, but yeah, that Lambdify is sort of the big one that you need to know if you want to do that.
Okay. Because to me, that seems like a really important bridge. You know, I've got this idea. Here's my theoretical equations, but at some point, I want to evaluate it and make the computer, you know, generate a graph based on these numbers or something, right?
Yeah,
cool.
definitely.
Cool. Well, good work on this project, you guys. It's pretty amazing.
Thank
and the explanation thing, Aaron, you had me pull out. That's really cool. How much it will say these are the algorithms we applied, and here's the little lesson to take from like why this makes sense here and so on. That's way better than just some sort of numerical integral. Like you gave me this function and no, it's 7.2 is the answer. Like, well, great, but what do I do with that, right?
Yeah.
Yeah. So maybe people could use it as a teaching tool, assuming.
Yeah, there are
of,
people who
something
use it in
people-
the classrooms, definitely.
Sure. Yeah. All right. Well, before we're done, let me ask you both the final two questions briefly. If you've got some kind of notable package, maybe it's not the most popular thing, but you know some Python package that's awesome that needs a shout out. There probably are a lot on this page already, and you've already given some, but anything you want to just call out real quick?
Well, so perhaps unrelated to SymPy a little bit, but
Yeah, it can be unrelated. Anything.
yeah. Well, I'd have to say one of my favorite packages that I use is this testing library called Hypothesis.
Yeah,
I'd actually like to make use of it in SymPy. We aren't using it right now, but I'd like to. But if you haven't used it before, the idea it sort of flips the idea of how you do tests on its head a little bit. Instead of sort of coming up with a bunch of examples and sort of testing that your function does the right thing on different inputs, you just sort of tell it what your function should do, and then it takes care of the job of generating examples. And the end result is that you end up testing a lot more of your code than you would with a normal test, and you end up with much more robust code as a result. So I recommend checking it out. It's called Hypothesis. I don't know if you've had Hypothesis on this podcast.
I have. It's been quite a while. It's been 3 or 4 years at least. But yeah, it's a very neat project, and I'm glad to see it's still going strong. I hear a lot about it. Andre?
Oh, well, I was going to say, do you want a Python package or any package?
Python, if you got one. If not, we can fall back to any.
Yeah, I was gonna actually Hypothesis also. I also discovered it kind of actually relatively recently. Yeah, I recommend people to check it out.
Which one? Sorry.
Oh, the Hypothesis.
Oh yeah. Sure. And I did talk about it way back in the day. This is 2016. Had David McIver on to talk about it, so that was cool. All right, and then final question: if you're going to write some code, some Python code, what editor do you use?
I use Emacs.
Emacs, right on.
And I use Vim.
Oh, and you guys still get along?
Yeah, of course.
No, just teasing. That's awesome. All right, well, thanks so much for being here. Final call to action. People are excited to get started with SymPy. Like, what do they do? How do they get started? Where do they go?
Well, so the easiest way is if you go to sympy.org, like you said, you can try it online. There's also a link there to download it. Yeah. Otherwise, I would say, you can, if you really want to dive in, you can join our mailing list, or you can follow us on Twitter. We're at SymPy, and yeah, Basically the easiest way to get it is to just pip install SymPy or Conda install SymPy, and you'll have it.
Nice. Andre?
Yeah, it's simpy.org or simengine.org. You can, if you like the C++ version.
Nice. And you have the tutorials that I highlighted. I'll link in the show notes so that you can go through on simpy.org as well. Fantastic. Well, really nice work. I love to see you bringing this to all the developers and data scientists and stuff. So thanks for being here and sharing SymPy.
Thank you for having us.
You bet.
Yeah, thank
Bye.
you so